So, Connor, or Cohen?
Connor is fine.
Cohen,
Yes.
flashbacks, what kind of mirror is it?
Convex.
Why?
Because it doesn't make a cave.
Okay. So,
Because you're small.
okay.
Yeah.
So, is there any way if I held this out that that image of me or you could ever flip over?
No.
Because virtual or real?
It's on the same side.
Virtual.
here.
Virtual. No, it's on the other side.
Oh, it's on the other side. Yeah, that's right.
Yeah.
You're right.
Okay, right? So, light's hitting, it's bouncing off, focal length positive or negative?
Negative.
Negative, because light's hitting and it's bouncing off. Okay, object distance, positive or negative?
Always positive.
Okay, just a quick refresher. Okay, that really wasn't part of the story, but, okay. All right, so yesterday you all figured out part of the frustration dealing with things that are charged. Because if we were all just made out of neutrons, we wouldn't interact with it, but if we were just made out of neutrons, we wouldn't be here anyway, because we wouldn't have any molecules or atoms that ever hook together. So it's kind of the trade-off. Because we are made of charged particles, we interact with that stuff. So yesterday you said, okay, well, what can we decide what's positive or negative? And at the beginning of the study of electricity, it's a good wise tale. If you go back to Ben Franklin, who did the experiment with the kite and the string, he had a basically 50-50 shot of getting it right in terms of how electricity flowed. He could either say, and again, this was in the, thank you, 1700s, thank you. So, they had, at that time, they had no knowledge of electrons, protons, and neutrons. So they kind of viewed the fluid or electricity as potentially flowing as a fluid. And so he coined the term like positive and negative. So he could either say the positive charges moved or the negative charges moved. And again, he had a 50-50 shot. Okay, that was it. He had a 50-50 shot. He chose to say, I'm going to make the positive charges move. Now, later on, you'll see in reality, he did not choose wisely, okay? It turns out it's the electrons that are moving. So, but we still stick with that convention, okay? And I'm going to tell you all now, in case some of you decide to flip out. When we start talking about circuits, we're going to talk about the movement of positively charged particles. We know it's wrong, but we stick with it, okay? We know it, don't argue, it's like, well, why? Because we do, okay? Just accept it. Just go with it, okay?
Yes.
Stop.
But it's
Stop.
Using them for it.
Thank you. So, I'm just telling you, when we get to circuits, don't flip out and go, Mr. Burkamp is actually, don't care, okay? Don't care. You're not going to change it. We haven't changed it in 100 years. We're not going to change it because you don't like it. So, when you all began to deal with the tape, okay, and you had to decide what's positive or what's negative, and literally, welcome to Ben Franklin's world is like, all I know is that there's charged particles. We don't know which side of the tape is positive. We don't know which side is negative. We're just going to kind of pick one, but we need to establish a framework. So one of the things you can do to establish that framework is that you can take a balloon and rub that balloon. Okay, where's the tape?
mystery powder.
So we can take that tape and put that on the table, pull that off, and so when I bring that near that balloon, it very much repels. So, what do you know? Because what's the only situation that something can repel?
Same charge.
Same charge, right? Now, hold that. But if I bring that tape towards my hand, it begins to attract. Does that mean my hand is positively charged?
No.
It just means that the chihuahuas are running away. So we say, well, is there a way we can actually quantify this? So what this device does, it looks like, you know, something out of a bad science fiction movie. So what this does is that it detects the value and magnitude of,
I'm just keeping it charged.
I appreciate that, of an electric field. So if I take the balloon and I bring that near that balloon, okay, you'll notice that that detects that negatively charged field. And that's why that signal goes into the blue region. This also nicely shows that it's an inverse function of distance. So when I'm way out here, okay, it basically doesn't have any charge. But as I bring that closer, it goes into that negative region, and the closer I bring it, the stronger the sense of that electric field is. Okay? So this is a way we can actually quantify it and go, okay, hey, it's negatively charged. So one of the things that they had to figure out is that how can we charge, like for example, these metal spheres? So there's a couple of options. So if I take yonder balloon and I just bring, this is a metal, this is going to be important, this is a conducting sphere. This is an insulator, it conducts. So I've got this negatively charged balloon, which we just established is negatively charged. If I bring it near, this is going to be important, I'm not going to touch it, okay? I'm just going to bring it near. I only have the one sphere. If I bring this close, okay, what's going to happen to the distribution of charges on the sphere? Jane Carroll.
Rearrange? I don't know.
So I'm going to bring this close. Is there going to be any change in the distribution of charges on the sphere?
No.
Really? So like if I put my hand here, why does it attract my hand?
Because it redistributes them.
So the chihuahuas run away from this side of my hand and the positive charges are left behind, right?
Uh-huh.
So if I take this balloon, which is negatively charged, and I bring it close to a conducting sphere, the chihuahuas that are on this side, what are they going to do?
They're going to move to the
So the chihuahuas are going to move to this side. What's going to be left behind?
positive.
Positive charge. So this is going to be important. If I don't touch it, if all I do is just bring it close, then all that's going to happen is that I'm going to change the distribution of the charges. Negative charges are going to move over here, so this side of the sphere is going to be negatively charged, this side is going to be positively charged. Cool with that. Now, we're going to do this, change this up a little bit. So now I'm going to put a conducting ruler in between the two of them. Okay? Now, I'm going to do the same thing. So if I charge this and I bring this, I don't touch it. This is going to be important. I don't touch it. If I bring it close, what's going to happen to those chihuahuas? Where are they going to go? So the chihuahuas, because I've got a bridge, is going to allow those to move all the way over here. So if I do this, I bring this close, and the sequence of this is important. If I bring this close, the chihuahuas on this balloon move over to the chihuahuas on that balloon, okay? This one closest to me is going to be positive or negatively charged. Positively charged. This one's going to be
Negative.
Now, if I take the balloon away right now, then what's going to happen to the charge?
They're going
They're going to equalize each other out. They're both going to be going back to neutral. Now, if I take this negatively charged balloon and I bring it close, and then I remove the bridge and then take away the balloon, now, can they go back to being neutral?
No.
So what's happened? I've created a negatively charged over there, and I've got a positively charged sphere here. So this is how I can make oppositely charged metal objects using a negatively charged balloon. But you have to have the sequence right, okay? So you've got to have a conducting material that connects the two, okay? You charge this, bring it close, that forces the chihuahuas over here. This is positively charged. I remove this, then I take it away. That's now negatively charged. This one is positively charged. Okay, so let me kind of discharge these. Now, I'm going to charge this again. I'm going to make this negatively charged. If I actually touch, this is going to be important. If I actually touch the sphere, then what's going to happen? Then it's going to be negatively charged. Why?
Electrons are jumping.
Yeah, the Chihuahua is going to jump ship. They're going to go, oh man, it's Taco Bell. Let's make the run from the border. So if I charge this and actually touch it to it, then this thing now becomes negatively charged. Even if I take this thing away, this thing is still going to be negatively charged. Now, if I do this, if I go back to having the conducting bridge in between them, if I charge it and I actually touch the first one, then what's going to happen? Then both of them are going to be negatively charged, because if I actually touch this, then those electrons are going to go from here across the bridge over here. Now, in which situation, assuming that you start back with all things equal. So situation number one, I have the balloon, and I just charge it, and I touch it to this one, okay? Negatively charged. So let's say this had, make up a number, 50 nanocoulombs of negative charge. If this had 50 nanocoulombs of negative charge, and I touch it to that, what's going to happen? 25 and 25, because Mother Nature likes to distribute things evenly. Let's make, this is method of my madness, let's make it 60. If this was 60, it would be 30 and 30. Now, if I take this and allow that to conduct between the two of them, and I start back up at 60, but now I do this, now how much is going to be on each one? I started with 60. I'm going to touch this and the bridge in between. Then how much is going to be on each one?
20.
Why 20?
Because there's 3 objects.
There's 3 objects, and that charge gets equally distributed between the 2 of them, or the 3 of them. So the more, if you have a certain amount of charge, the more objects that you distribute that between, what's going to happen to the charge on each one? That's going to become lower and lower and lower. Got the idea? Good? Great. Back we go.